My name is Diana Parno, and I'm an experimental neutrino physicist. Neutrinos are strange particles. They're very difficult to detect, but they've already revolutionized the way that we think about particle physics and astrophysics. Our remaining questions about them: how much do they weigh? Are they their own antiparticles? How exactly do the different neutrino states relate to each other? And how do they interact with other kinds of matter? These all promise still more fundamental changes. I use nuclear reactions as a tool to learn about neutrinos, and I use neutrinos as a tool to learn more about nuclear physics. I work with large international teams of about 100 people each to build, run, and analyze sophisticated experiments that advance the state of the art both scientifically and technically. So take that first question: what does a neutrino weigh? I've risen to become a leader in the Katrin experiment, which, beginning next year, will study the radioactive decay of tritium to probe the neutrino mass with unprecedented sensitivity. As analysis co-coordinator, I work with students, research fellows, and faculty from 6 countries. We want to ensure that our results are robust, that we fully understand the way our equipment operates, and that we have control over the inevitable uncertainties in our experiment. I lead a group of 5 graduate students, 3 of whom are women, and I've given scientific talks in 4 countries. Now I want to extend my leadership by taking on a bigger role in a different experiment, Coherent, at Oak Ridge National Laboratory. Last year, our collaboration made the first ever discovery of coherent elastic neutrino nucleus scattering, or SEVNS, a type of neutrino interaction that scientists have been dreaming of detecting for more than 40 years. SEVNS is challenging to measure, but tremendously exciting. It affects the way that supernovae release energy. It's a critically important input for next-generation searches for dark matter. It gives us a new way to investigate nuclear structure. And because you can calculate it so cleanly, it's an exquisitely sensitive test for physics that falls outside our established theories. The Coherent collaboration is now trying to approach these questions with very accurate measurements of how likely SEVNS is to happen for several different chemical elements. But for that, we need to know how many neutrinos are actually produced at our source. My student Rebecca Rapp and I have been trying to answer this question, but our methods depend on nuclear physics that we just don't know accurately enough. That's why we'd like to work with our colleagues to build a heavy water detector to carefully measure the neutrino rate using interactions that are already well understood. At our lab at Carnegie Mellon, I'll work with Rebecca and with undergraduate researchers to develop and test critical components before they're assembled into a working detector. With Johnson & Johnson's help, we can make this new chapter in neutrino history even more exciting. Thank you.